Welcome to the AP Physics Workbook solution. Here we have Unit 3, Circular Motion and Gravitation. Here we have the Section 3.0, the Gravitational Force. All right. Here, the scenario, Angelica, Blake, and Carlos are studying the data table to the right, which shows the mass, orbital radius, and orbital period for 4 planets. They note that the orbital period increases but decreases. About why this happens. Their arguments are the following. Okay. First of all, you're going to create an equation. We're not going to worry about this until the bottom part, which is just the argumentation. But to motivate this idea, but by the masses, right? Look at the masses, right? Look at the orbital radiuses. To motivate this, I would like to show you a clip from Family Guy. Okay?
See this?
Yeah.
You know what it is?
Duh. It's an apple.
Good, good, good. All right, watch this.
What the hell? What is this? What is this, some kind of gag?
No, that's orbit.
Huh?
You have your own gravitational pull.
Oh, that's a bunch of crap.
Now back to the three.
All right. So depending on the masses of the object, there's going to create a gravitational pull just for that idea. All right. So, and again, we're going to start this. The deviation that I'm going to go over here is going to be very quick because you should already have seen this in part 3N. 3N will give you this deviation in more detail. This time, I'm going to show it very straight. Okay. So here's step 1. All right, so let's just zoom in here. Step 1 is going to be just the force of the equation. Force of gravity is defined by G, gravitational constant, right, times the mass. And here we are looking for what planet? A mass of the planet. Right? And do we have the masses of what? Mass of the planet and the orbital of the object. So mass m, and the other one we are going to have as small m. Okay. Okay, yeah. All right. So the first one, I just want to make sure the notation's right. All right. So mass of the big planet, m, and this is going to be the small mass of the orbit. So I'm going to use this small m. Okay? All right. That's going to be divided by the radius squared. Okay? All right. Again, let me just note this for you. Big M is the mass of planet, and the small m is going to be for the satellite. Okay. I don't know how to spell that. Okay. All right. So here's the second step. You know that this m r squared has to be equal to ma, which is centripetal. Okay. We already know that though. That is the oh, what mass is this? Oh, it's the centripetal acceleration caused by the planet. So this is big mass. So this is the big mass. All right. Okay, this is the big mass. This is the small one. Right? So that's going to be v squared over r squared. Here's the third one. Okay. This should be the same r, so I use big R. All right. Oh, sorry. It's R, big R. It's just v squared over r, remember? Okay. All right. So third step. Okay. Certain things can cancel out. All right. So I'm going to divide by m. So let me show you what's going to be happening, right? I'm going to divide, so I'm going to multiply by 1 over m. Multiply by 1 over m. Okay, then I'm also going to multiply by r over 1 and r over 1. All right, that's where the cancellations occur. That's why the next step should look like this. G, okay, and you have your small mass, that's what's left, and you only have one r here, and this is going to be equal to m, big M. Oh, no, no, big M canceled. So the only thing that you have left here is v squared. All right, okay, so that's what this is. All right, so I'm just going to take out the algebra here, but you should understand where that algebra is coming from. Okay, again, look back at the previous problem, right, in the text, um, in the book, if you would like for me to show you where it is. Okay, good, good, good. If you have any questions, please let me know. All right, so next part. From here, we need to get period. Okay, so we know that the t, we've already should be used to this substitution. V is equal to 2 pi r over t. So you're going to plug that in. You're going to have, for step 4, g, again, this is small mass, over r is equal to, again, this squared, right? When you plug it in, you know it's squared. 4 pi squared r squared over t squared. Again, look back at 3n if you would like a more detailed explanation on this. Right? Okay, that's 4. Step 5, certain things cancel out. So cross multiply, you should get t squared is equal to 4 pi squared r cubed over g little m. All right. Step 6, now you want t alone, so square root it. 4 pi squared r cubed over g little m. There you go. 6 steps, right? 6 steps, okay? If you would like to see the complete detail, look at 3.n, and I go through a long deviation of this in more detail steps, okay? But that's it, right? So now the argument. So let me just bring this up, back up, and we could probably just do it if we compare them, right? Yep, looks good. Yep, argument. Perfect, yeah, sweet. All right, so Angelica, so you work in part A to use to support or refute the argument of each 3 students. For each student, explain which aspect of their reason is correct, if any, and cites evidence from part A and explain how the student steps support or refute each claim. All right, so Angelica says, it appears that the more mass an object has, the longer its period is. This is because more mass objects are more difficult to move, so these objects move slower in orbit. Well, orbital period is how long it takes an object to go around, right? That doesn't make sense because remember, mass always canceled. If you look back at all the other problems you did in this section, mass always cancels, right? So here, wow, Angelica, you're bad. Okay, so let me write here. So let me bring up Word and I can write it for you. So, all right, so you would write, okay, Angelica is wrong. Okay. The mass of the planet has no effect on the orbital period. The mass of the planet cancels out in the calculation. The orbital period only depends on the radius. All right, we should have that. Let me just change this. Perfect, and boom, boom, boom. calculation, independent. Yeah. Okay, looks pretty good. All right, and bring it over here. No, that looks ugly. So let me. I'm trying to bring it. So this is why Angelica's wrong, right? So I'm just gonna write it right here, okay? So this is what Angelica's wrong, all right? Okay. So boom. For this is Angelica's, okay? All right. Good. So let's look at Blake's now. All right. So here, let me orbit the pair. Yeah. So good. All right. So you could see it a little bit better. Let's look at Blake. No. All the planets move at the same speed around the sun, but planets with greater orbital radius, yes, yes, that's correct, must make longer circumferences orbit because the orbit period has to be greater. Oh, that is very interesting. So, all right. Good, good, good. So here, he is correct, right? Okay, so let's see. But planets with greater orbit radius must make longer circumference or orbit, causing the orbit period. Not all planets move at the same speed around the sun, but planets with greater orbit radius must take longer circumference orbits. All right. So, um, right here, let's see. Okay. Okay. So from here, let me show you something here. Okay, so you would write here that Blake is also incorrect in explaining the speed that a planet orbits the sun depends on on how far it is from the sun. Okay, so that is wrong. Okay, it's not how far it is from the sun. It depends on its radius, right? Okay, so it depends on the radius away from it. You're going to see much better when I show you the example, okay? All right, so here, all right, he is correct in the thinking that a larger radius, okay, will, he is correct in the thinking that a larger radius, okay, will have a longer period. Right? That is correct, okay? Because the object has to travel farther has to travel further, okay? Travel further. So for the object to have the same period but traveling further, the object speed must increase. Okay, that's it. All right. So this makes sense. Give me a second. So the best way to think about the way Blake is explaining is if you look at a track meet, right? Notice that around the track, the runners are at different positions. Like they say, they start in different spots because they end up running the same. They want to make sure they're running the same distance, all right? So the further away you are from the center, the more distance that you have to cover. So, like what it says here, you have to travel further. But if you want to come back at the same time, right? Like if these guys all here want to cross the finish line at the same time, okay? The runner at the end, right? Okay, the runner at the end actually has to like, so let's say they all ran a straight line, right? Let's see, do I have a picture of that? Let's see if they all ran at the same starting position, okay? Right? If they're all straight like this and they want to come into the end where it's all straight like this, okay? The person at the farthest end had to run more. So the further you are from the center, you have to basically run faster, okay? All right. Let's look at Carlos. Carlos says in the case that the farther radius planet must make the farther circumference orbit, but the farther planet also goes slower because there is less gravitational field on them. Well, that is correct. Yeah, Carlos is correct. Whoop. Let's bring up backward. So we would say that, yeah, Carlos is correct. Right? The farther circumference orbit. Okay, Carlos is correct. The farther circumference orbit. Carlos is correct. The further orbit means the object is going to feel less of the gravitational pull, right? Okay. And there is a slower speed for that planet. Yep, that is correct. All right, so good. All right, so before I end, this is basically it, but I would like to show you how this is in relationship to a very crucial idea, because all these ideas come from Kepler's law of planetary motion, okay? So I want to show you a couple of clips from this video to help you, okay? All right, so what I have here is the video, okay? The two Kepler's laws are very important, the second one and the third one, okay? So listen up. If you would like more details, just watch the full video clip, okay?
The law of areas. Kepler's second law states that the line joining the Sun and planet sweeps out equal areas in equal intervals of time. For example, the area swept by the Earth in March and April equals the area swept in May and June. Kepler's third law, the law of periods. Kepler's third law is concerned with the time period of revolution of planets. It states that the square of the time period of revolution of a planet in its orbit is directly proportional to the cube of the semi-major axis of the elliptical path around the Sun. For a circular path, t square is proportional to the cube of the radius of the circular path. For example, for Mercury, the length of the semi-major axis is 0.39 astronomical units, and its time period around the Sun is 0.24 Earth years. For Mars, the length of semi-major axis is 1.524 astronomical units, and the time period of revolution around the Sun is 1.88 Earth years. Observe that the ratio of the square of the time period to the cube of the semi-major axis is almost the same for both the planets. Summary.
Okay, good. And I'm going to show you one more thing. Hold on. All right, so this video is actually what I wanted to show you, okay? This is actually the one that I use so much to just understand it, okay? So listen up, all right?
States,
The line joining the planet to the Sun sweeps over equal areas in equal time intervals.
When a satellite orbits, the line joining it to the Earth sweeps over equal areas in equal periods of time. If areas 1, 2, and 3 are equal, times 1, 2, and 3 are also equal. Therefore, the speed of the satellite changes depending on its distance from the center of the Earth.
You see, right? That should make so much sense to you. Again, rewatch that if you would like to see its importance, okay?
Speed is greatest at the point in the orbit closest to the Earth, called perigee, and is slowest at the point farthest from the Earth, called apogee.
You don't need to remember these words, the name, right? But exactly what it says. It's what? Exactly what it says here.
Point farthest and is slowest.
Listen.
Speed is greatest at the point in the orbit closest to the Earth, called.
Right? Speed is greatest when it's close, okay? Because of the R.
Perigee, and is slowest at the point farthest from the.
And when R is great, right, the gravitational pull is less, so it is slower.
The Earth, called apogee. It is important to note that the orbit followed by a satellite is not dependent on its mass.
Right? Not independent, right? The orbit does not depend on its mass. That's why mass canceled in all of our calculations.
A large, heavy satellite could be in the same orbit with a small, light one, each sweeping out equal areas in equal periods of time. Kepler's third law, the law of periods, relates the time required for a planet to make one complete trip around the Sun to its mean distance from the Sun.
For any planet, the square of its period of revolution is directly proportional to the cube of its mean distance from the Sun.
Applied to Earth satellites, Kepler's third law explains that the farther a satellite is from the Earth, the longer it will take to complete an orbit, the greater the distance it will travel to complete an orbit, and the slower its average speed will be.
Okay? That's it. Those are all the important piece of information that you should know for the gravitational force. All right.